Swayam Prabha. Digital India. Educated India.
Hello everyone. Today's topic is construction of shape function for two-dimensional finite element. You see, construction of shape function is one of the very important steps in finite element method, because once we have the element and then we substitute that element in the weak formulation, it is the shape function which represent that element. In the last class we had seen that approximation error is one of the major source of error in finite element method, and we had also seen that finite element method, the convergence of finite element method, rate of convergence of finite element method depends on the approximation. It depends on the degree of the highest degree of complete polynomial present in the approximation. So far in the first class we also tried to derive the shape function for a constant strain triangle, three-noded triangle, which is the most basic elements in two-dimensional element library. And there what philosophy we used, we took an approximation and then the unknown constants are determined by imposing the interpolation condition, interpolation of the primary variables. This is the same approach we followed while determining the shape function of 1D bar element, shape function of two-noded bar element, three-noded bar element. Here, when we invoke the interpolation condition, it is the interpolation of the primary variable is important for us. And thus, through that the shape function what we get, we had seen in the last class again, that this shape function give us the global level, the global continuity of this shape function approximation is C0, which is the minimum requirement for a finite element approximation. These families of element where only the primary variables are interpolated are called Lagrange families of element. Again, two-node bar element, three-node bar element, and then constant strain triangle in the last class. These are all the family of these, the member of these families. There are many cases where we cannot afford to have only interpolation of primary variables. We had seen in the case of beam. We will also see in the case of plate and cells problem where the derivatives are also need to be interpolated. The continuity in the derivatives are also important, and those elements are called Hermite families, the member of Hermite families. Now, today's discussion we will restrict ourselves only to elements of Lagrange families where the primary variables are interpolated at the node. Okay. Now, so if you recall in the last class when we talked about completeness, we introduced the Pascal's triangle, and the triangle what you can see on your screen, this is the same Pascal triangle. This is also called Lagrange simplexes for triangular element. And what it tells you, this Pascal's triangle, suppose if I want to have a three-noded triangle, then in the approximation the term I must include is 1x and y. So for this our approximation should be u is equal to some constant say c1 plus c2x plus c2y, and this is the approximation we had taken while deriving the shape function for this element. Now similarly, if we have to derive the shape function for this element, these are the which is quadratic element, which is also called linear strain triangle. Now for this we have to take all this term we have to take. Okay. Similarly, if we have to take this, for deriving the shape function for this element, we have to take all this term. So if you compare this triangle with the position of the nodes in the Pascal's triangle and the positions of nodes in the element, you will see that every node correspond to one entry in this triangle, in the Lagrange simplexes. Okay. So this gives an idea that when we have to construct a safe function for these kind of elements, then what should be our starting point, our starting approximation. Now, similar thing can be done for quadrilateral elements, which are called Lagrange hypercubes. But then here the previous triangle is represented slightly different way. Now, what this tells you, suppose if you want to construct these safe function for this, which has 4 nodes. Okay, so this is our safe function. This is our safe function for that. And for this safe function, what are the elements? What are the monomial to be taken in the approximation? This will be that C1 plus C2x plus C3y and plus C4xy. These are these 4 terms to be taken in the approximation. Now, if this is the element, and for that we have to construct the safe function, then these are the element. And similarly for say this element where we have 1, 2, 3, 4, 5 nodes every side, then the entire thing we have to take. This is not the entire thing. You can keep on writing, extending these simplex hypercubes. Okay. Now these will be our element. So again, every node correspond to the entity, one entry in this triangle. Okay. Now what we do before we start, we had already seen the construction of safe function for the most basic element, the triangle element. Now let us in this family means in the quadrilateral family. Now this is the most basic element. Now let us first find out, derive the safe function for this, following the same approach that we adopted in case of triangular element, and then later we will see if we have a higher order element, then how to construct the safe functions. Okay. Now, so this is the element we have now, the 4 noded rectangular element. Now these are the coordinates at every nodes, and then these are the function values at the nodes. Okay, we have to start with an approximation. Now polynomial approximation is this. Now if we have seen in case of this element, these are the terms that we have to take. We have to take one constant term, then x, then y, and then xy. Okay, this is the approximation. Now you may say that this is not the complete, this is not a quadratic approximation, though we have xy term in this expression. This is not a quadratic approximation. This is called bilinear approximation. Okay, so if you have to comment anything on the completeness of this approximation, it is a linear completeness we have. Okay, because we have taken all the term required for up to the first order completeness the approximation has. Okay. Now, so the same steps we have to satisfy these approximation at every nodes and determine the C1, C2, C3 and C4 constants, and then if we do that, then our final safe functions will be like this. We have skipped this exercise because it is now going to be exactly same. We have already done this exercise in case of triangular element. So this is the safe function for a rectangular element. But you see, this is a very, very tedious process. If you look for rectangular elements, though it is fine, but you think of when we construct safe function at the higher order elements, here we have to invert a 4x4 matrix. But if you have an element like this, or element like this, even for element like this you have to invert a 9x9 matrix every time we construct the safe function. Here you have to integrate a 16x16 matrix. So this process is a very tedious process. We need to think of something which is more sophisticated, more elegant to construct safe functions for these kind of element. Okay, this is the plot of the safe function. Just now we have derived this, these are the expression of the shape function, and if we plot it, this is how the shape function look like. This is not a very new thing to us. We have already seen these are the properties of shape function. It satisfies the Kronecker delta property, and at every element, every node, every shape function at that associated node, these values will be 1, and all other places it will be 0. Now you can verify whether it satisfies partition of unity property or not. Now there are two things. First, we have seen this approach is tedious, especially for higher order elements. But then another important thing is, one of the major advantage of finite element method is we can deal with complex geometries, right? We may not have always a geometry which can be divided into elements which are rectangular. Okay, so we can have a geometry for which the elements may not be rectangular. So if we follow this approach is in those cases will be extremely tedious. Okay, for instance, just to look at it in a proper perspective, suppose this is the finite element discretization of some domain, and take any arbitrary element from this entire thing. Let's take this element, and if we just zoom it, this element look like this. Okay, now this is first of all, this is orientation is different. This is not a problem, but it is not a rectangle. Okay, now so we have to eventually deal with this kind of element. How to construct shape functions for element which are not rectangular? We have to see that. What approach we will follow here is, okay, this is in xy coordinate system. We have this element, and this is our physical domain. Okay. Now let us define a domain. Let us define an element which is a square element. Okay, in this element it has 4 nodes. So in this element also has a very idealized element. This is our idealized element. This also has a 4 node. Okay. Now the coordinate of this element is, say, it is xi and eta coordinate. These elements in a x and y coordinate, this is xi and eta coordinate. These coordinates are also called local coordinate. Now this domain is called parametric domain, and the domain is -1 to this, and xi eta are called natural coordinates. This domain, this means if you coordinate of this is -1, this is -1, -1, this is, say, 1, then -1, this is 1, 1, and then finally this is -1, 1. So our domain is this. This is our parametric domain. Okay. Now this element is called physical element, which exists in the real structure, and this is our idealized element. What is to be done with that element, we will see shortly. Suppose we define an elements like this. This element is parent element. Okay. Now what we do is we define a map between our parent element and the physical element, or between parametric domain and a physical domain. We define a map like this. How to define a map, we will see. Now this, we will not go into the details of this map. Next week we will be talking about isoparametric formulation, and there we will see that how to define this map. Okay, we will do that. Now so this is what idea is here. We construct our shape function on the parent element, on this element, and constructing shape function on this element is relatively easier because our parent element is always as a square, -1 to 1 and then -1 to 1. So we will construct our shape functions in this element, in parent element, then entire thing will be mapped to the physical element through a transformation. And what is that transformation? We will discuss that in isoparametric formulation next week. So what we do today is we forget about this transformation, and this we will restrict ourselves to construct shape function only on parametric domain. Okay. So next 15-20 minutes we will discuss construction of shape function within for a parametric for a parent element, and this parent element could be a 4-noded element, it could be a 8-noded element, it could be it could be element higher order element, but the point is, irrespective of the order of the element, our parent element is this. Our construction of the shape function will rest in terms of the natural coordinate, in terms of xi and eta. Now once we have the shape functions with us, next, while discussing isoparametric formulation, you will see what to do with the shape function that has been constructed on parent element. Okay. Now there are some example of the parent element and the corresponding physical element, you will see. So this is the linear element and this is the corresponding element in the physical domain. This is a quadratic element. This is the corresponding in the physical domain. Now interesting thing is, you see in this 4-node, if you look at the sides of these elements, this side is a linear side, this is linear, and where if you have one extra node here and on the sides you have 3 node, then you have quadratic domain. So with this you can represent the domain in a better way. Okay. So similarly we can have this element as well. Now our objective is to construct shape function for this element, shape function for this element, shape function for this element, or similar kind of element, but in terms of natural coordinate. Okay. Now let's start with this. So this is the element, physical element. We have already seen what is the expression for the shape function, and the expression of the shape function are this. AE is the area of this element. Okay. Now this map is very straightforward, from a rectangle to a square or the square to a rectangle. What we do is, this expression is written in terms, these shape functions are written in terms of nodal coordinate. So here we know the nodal coordinates are this. We will substitute this nodal coordinate in this expression and then replace x by xi and y by eta. We will get shape function of this element in terms of natural coordinate. Okay, and this will be this. So x is replaced by x2, x is replaced by xi, and y is replaced by eta, and area is replaced by 4, because here the area of this parent element is 4. So these will be the shape function. Now if we substitute at every node, if we check, we will see that these shape functions satisfy the Kronecker delta property, it satisfies the partition of unity property and all. So together, combinedly, if you have to write the shape function for this is like this, where xi I and eta I are the coordinates of ith node. For instance, if I have to construct shape function for 1, I is equal to 1, so it will be 1 by 4 plus xi 1 into xi 1 is minus 1, so it will be 1 minus xi plus 1 plus eta into eta 1 is minus 1, it will be 1 minus eta. So this is the expression. So this is how we can write this shape function in a compact form, right? So this has been very straightforward. This transformation has been very straightforward. Now, but this may not be the same for higher order elements. Suppose if we have an element like this is our element. I want to construct shape function for this, construct shape function for this higher order element. What approach to be adopted? There we introduce a method called where we construct the shape function through tensor product of shape function constructed in one dimension. For instance, suppose this is our element. Let us first understand the method with this element and then extend the same thing with other elements as well. So suppose I want to construct the shape function for this element. Okay. Now assume we have one dimension element, 2-noded element like this in xi direction, in this direction. This is xi direction, and this 2-noded element is between -1 and 1. And then assume another element in eta direction, again 1, 2 are the corresponding nodes, the element level nodes for this element. Here 1, 2 are the element level nodes for this element. Now this is in eta direction, this is -1, 1. Now we already know what is the shape function for this element in one dimension. We already know what is the shape function for this element. What are the shape function for this element? This is the shape function for this, and this is the shape function for this. And how the shape function is represented here is phi 2L1. Phi 1 stands for it is corresponding to node number 1. This node number 1 is in element level for this element, and phi 2 is shape function for associated with node number 2. Again, this node number 2 is the element node. Then phi 2L means it is two noded linear shape, two noded line element we have. That's why it is written like this. Similarly, here also the shape functions are it is phi 1 because it is corresponding to node number 1, and phi 2 because it is corresponding to node number 2, and 2L because it is two noded line element. So this already we know, right? Now what we will be doing it, we'll take the product of this, tensor product of this two element. Now if we take the product of this, we will get shape function for this element. Okay. Now first let me write the expression, and then we will show how this product to be taken. So this is our shape function at the for 4q means it is 4 noded quadrilateral element which is a function of xi and eta. In this case it will be function of xi only, and in this case it will be function of eta only. Okay. So this is the shape function for this quadrilateral element, and this will be written as this, where ij is the dyad, and what it means I will come to that shortly, and this equal to this multiplied by this, where this is phi I2L means this is the shape function for ith point, ith node, but this ith node is the element level node. Similarly, phi j2L is a function of eta. It means it is the shape function of this element, but this is at the jth node, and jth node is the element level equation. For instance, if I have to calculate the shape function of node 1, so phi 1 this is phi 1, say phi 1 4q, then xi and eta, that will be equal to, now 1 means this node, right? And in this node, what are we have from this element, we have this node, and from this element we have this node. So at this node, this dyad will be 1 1. This 1 correspond to this node, and this blue one correspond to this node. So this will be is equal to, this will be phi 1 2L, which is function of xi, into phi 1 2L function of eta. So this shape function will be this multiplied by this shape function. So this shape function and the product of this shape function. This will give me the shape function at this node. Similarly, suppose I have to find out the shape function for second node. So phi 2 4q means it is for the quadrilateral. This is function of xi and eta. This will be for this node. What will be this dyad? We have node number 2 from this element and node number 1 from this element. So the dyad will be node number 2 from this element and node number 1 from this element. So this will be phi 2 2L, which is function of xi, and then phi 1 2L function of eta. So this shape function will be this. Similarly, if we have to find out shape function for this, then dyad will be from this element we have 1 and from this element we have 2. So okay, this is for so this will be 1 2, and for this node it will be 2 from this element, 2 from this element, it will be 2 2. This is how we can construct the shape function. Now you see, this shape function is constructed just based on the information already we have from from analysis of one dimensional problem. While constructing the shape function, we didn't have to write an expression, then invoke interpolation property, and then find out the unknown constants. Now let us understand visually how it is. So suppose this is the we have understood now how to construct the shape function. Suppose this is the element, the same element, just for better visualization, it is shown like this. Okay. Now suppose I want to construct shape function for this using the tensor product of shape function of this element. Now let's do that. So this is our this element, and okay, and this is coordinates is -1 to 1, and this element is again it is -1 to 1. So this is xi direction and this is eta direction. So this is our xi direction and this is our eta direction. Okay, two direction. Now what is the shape function? We want to construct shape function at node number 1. As a node number 1, our diode will be 1 from this and 1 from this. So at this, in this element, shape function for node number 1 means phi 1 will be this. This will be phi 1 12, and then from this element at node number 1, our shape function will be this. This is phi 1 12. These 1 1 are the local element level node numbering. Then we have to take the product of this. Okay, and if we take the product of it, our shape function become this. Shape function become this. So this is our shape function. The similar thing we can do for other nodes as well. Let's do that. Okay, so this will be our shape function, right? Now we already we know that the shape function for this 1D element will be within in -1 domain will be 1 minus xi by 2. You can check xi is equal to -1, phi 1 is 1, and xi is equal to 1, phi 1 is equal to 0. So this subfunction is this. And similarly, phi 1 2L can be written as this. It is a one dimensional it is written like this. Now you have to take the product. So this will be this and this into this, and if we take the product, this product will be this. So this will be our shape function. You can verify that by invoking the interpolation condition at the nodal level, starting with an approximation, invoking the interpolation condition to determine the unknown constants, and then writing the expression for shape function, we actually had the same shape function. But now instead of doing all this exercise, we could write the shape function directly from the information of one dimensional element. Same thing can be extended to higher order element as well. Let us do that. For instance, this is our element. Okay. Now this is, see, in actual structure, if we look at this in the actual structure, this element could be like this. These are the nodes. Okay, these are the nodes. This is the physical element, and this is our parametric element. In actual structure, the element may look like this, but as I said, our concern, we are not bothering how it looks like in the actual structure and what is the map between the physical element and the parent element. However, here focus is to construct the shape function, finite element shape function for the parent element in terms of natural coordinate. Okay, so that's why these are all line. This is not the curved. Okay. So this is the one dimensional element in xi direction, 3-noded element, and again this is 3-noded 1D element in eta direction. Okay, and then we know these are the shape function. We have already seen 3-noded bar element, what are the shape functions. Similarly, we can have a shape function like this, and if you take the product of this, we can get the shape function of this. Okay, so this will give you I and this will give you j, and our shape function will be this phi k 9q because it is 9-noded quadrilateral, which is a function of xi and eta, and this will be your phi 9q, and then diode will be ij, and I comes from this element and j comes from this element, and this is function of xi and eta, and then this will look like this. This is the shape function from this, and this is the shape function from this. Okay. Now this probably gives a better visualization. Suppose this is the element we have. Now, not necessary. Once we have this a general approach, not necessarily that we have to have the same number of node in xi direction and eta direction. For instance, in this element, if you see, in xi direction we have 4 node, and in eta direction we have 3 node. So in xi direction we will take a 4 noded line element, and in eta direction we will take 3 noded line element, and then we will take the product. And for in the xi direction, if you see, these are the different shape functions for different node. Phi 1 is the shape function associated with node 1, phi 2 shape function associated with node 2. At node 2 it is 1, all other point it is 0. It is for node 3 and it is for node 4. Okay. Similarly, these are the shape functions for 3 noded line element. This is for node 1, this is for node 2, this is for node 3, and if we take the product of this, it will give us the shape function at different points. Okay, following the same approach just now we had discussed. Okay, now the question is, see, we based on the discussion in 1D problem, we already know the shape function for a 2 noded element and shape function for a 3 noded element. Now in this problem we have shape function for, we need shape function for a 4 noded element, but theoretically we can have an element like this. Okay, you can extend it, you can put any number of nodes here. So this is an element which is which has 36 nodes in this element. So in xi direction, if we see, we have 6 nodes, and eta direction we have 6 nodes. So we need to have a shape function for this element, 1D element, and we need to have a shape function for this element, and then take the product to get the shape function for this element. Okay. Now shape function for this element can be obtained from Lagrange polynomial, and Lagrange polynomial was introduced to you while during the discussion of formulation of shape function in 1D for 1D element, and how it looks like in compact form. This gives you the Lagrange interpolation function. The property is it interpolates the value. It has a Kronecker delta property. So if we write it, if we expand this will be something like this. This is the compact form written, and if we expand it, this will be the form. So n is the number of points you have in the element. For instance, in this case, we need to write the polynomial for this Lagrange interpolation. For this, we have in this case n will be 6. Similarly, in this case n will be 6. If we go back, for this problem, for this element we have 4 noded. So when we compute the shape function using Lagrange polynomial, for this n will be 4, and for this direction when we compute the Lagrange polynomial, in this case n will be 3. Okay, so this is the Lagrange polynomial we already know, right? This will give us the interpolation function for any number of element in one dimension. Okay, so now let us write the interpolation function in xi direction and interpolation function in eta direction. Interpolation function in xi direction will be this, and eta direction will be this, where n xi will be the number of nodes you have in xi direction, and n eta is the number of nodes we have in eta direction, right? And then this interpolation will give us fi n xi l. N xi l is, it will be, suppose if you have, if n xi is 2, means if you have 2 nodes in zeta direction, this will give us phi I to l xi, and this will give us phi j to l eta. Phi I to j and phi j to l, this is the notation we already used, we had seen it. So this is how we get this component in xi direction, in eta direction, and the next is to take the product of these two component to get the shape function at any for any particular dyad. So if we are taking, if this is 1, say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and similarly this is 1, 2, 3, 4, 5, 6. If you are constructing shape function for this element, this node, then our dyad will be 3 and then it will be 3. If you are constructing shape function for this node, this our dyad will be 5 and 3. So this is how we have to calculate phi I and phi j and then get the shape function. Okay. Now, so this is how we can construct the shape function for any number of nodes we have in the element. Now, so next what we discuss is we have not done any particular example because now the implementation of this is a very straightforward. Okay. Now, see, look at one important thing in these elements are that we have these nodes, intermediate nodes, right, within the element nodes. Now we will talk about another class of element which is called serendipity element. This is the Lagrange, not Lagrange family, this is Lagrange element. Okay. Now the serendipity element is when you take these intermediate node out from this element. Okay. For instance, we remove all these nodes we have within the element. If we remove this, then this will be these serendipity elements. Okay, the serendipity means that development of something by chance, right? And the word itself, the serendipity, the word itself came from the story of three princes of Serendip. So we will see shortly. See, we cannot apply Lagrange, the approach that we adopted while for the construction of a shape function in Lagrange element. Same we cannot adapt here because that will give us intermediate nodes within the element. Okay. Now, this was the serendipity element was and the isoparametric formulation. It was proposed in 1968. Now, the development of serendipity element and the isoparametric formulation probably is a remarkable thing happened in finite element method, and it made our life much easier to apply finite element method for a more general class of problem, general with complex boundaries, and we will see that. We will see in the next class what is isoparametric formulation, but today we will see what is serendipity element and how to construct the shape function. As the name suggests, it's a development by chance. In this paper, Zinckwich, the shape function is constructed just by inspection, just by looking at the elements and invoking some of the properties that we want in the element. For instance, let me first compute the shape function for this. This already we know this shape function for this element, but now we will follow a different approach to shape function, and then that approach will apply for this element. Otherwise, if we apply the approach just now we discussed, taking the tensor product, we will not get the shape function for this element because we have then one intermediate node, one node within the element. Now let us see how we can construct the shape function. Take this element, 4-noded element. This is the element we have, right? And these are the nodes. And the coordinates are, this is minus 1, then 1, minus 1, minus 1. And this is minus 1, minus 1. Then we have 1, then minus 1. Then it is 1 and 1. and it is minus 1 and 1. Okay, and suppose this is node number 1, this is node number 1, this is node number 2, and node number 3, and node number 4. Okay, so initially we discussed that we take a polynomial, then the constants, determine those constants by invoking the interpolation conditions, and which required inversion of 4 by 4 matrix. This was our first approach. And the second approach we discussed is, okay, we know the shape function for two noded element, bar element. Now if we take the tensor product of these two, tensor product of two noded bar element, two noded bar element, we'll get the shape function for this. Okay, now now our approach will be slightly different. And what is that approach? What we know? See, suppose I want to find out the expression for n1. Now what properties this n1 must satisfy? Okay, important property is Kronecker delta property, the interpolation property, because that is the only criteria we use, that is the only constraint we use in Lagrange elements, right, in the elements in Lagrange family. Now, so for n1, the information we need is, for n1, that one criteria is n1 should be equal to 0, n1 should be equal to 0 at xi is equal to 1. So this is one criteria we have. So xi is equal to 1 means, let us see the xi and eta coordinate. So this is xi coordinate and this is our eta coordinate, right? So this is xi is equal to 1 means, on this line, on line 2, 3, xi is equal to, and on line 2, 3 it should be equal to 0. Okay. Now the second, because on line 2, 3 you have node number 2 and node number 3. Now second condition, what we have? Second condition, we have n1 must be 0 at eta is equal to 1. Eta is equal to 1 means on this line 4, 3 and 4. This is the second condition. And what is my third condition? Third condition is n1 should be equal to 1 at node number 1, and node number 1 is xi is equal to minus 1 and eta is equal to minus 1. So these three conditions, interpolation, this is the interpolation property, right? Now by just looking at it, this condition to be satisfied, this condition to be satisfied, this condition to be satisfied. Now let us assume an expression for n1, say n1. What, since n1 should be is equal to 0 at xi is equal to 1, the expression of n1 must contain 1 minus xi term. Since n1 is equal to 0 at eta is equal to 1, expression of n1 must contain 1 minus eta term. Okay. And then some constant c. So if we take an expression of n1 like this, you see this condition and this condition is satisfied. Only now this condition needs to be satisfied. Now this condition is what? C, we don't know what is the value of C. C will determine so that this condition is also satisfied. So n1 at xi is equal to minus 1 and eta is equal to minus 1 is equal to 1. So this gives us, if you substitute xi is equal to minus 1, it is equal to minus 1, it will be c into 2 into 2 is equal to 1. This gives c is equal to 1 by 4. So this gives us n1 is equal to 1 by 4, 1 minus xi and 1 minus eta. Now look at you compare this shape function that we obtained following the other two approaches just now we discussed. We got the same shape function, right? The same thing we can do for 2 and 3 and 4 other nodes as well. But this is the element for which we really do not need this approach, right? Now let's apply the same approach for this element, the quadratic element. Okay. Now let's do that. Now our shape function has our element is like this. And we have, these are the nodes we have. Then we have at the end. Now I have not mentioned anything about the numbering of nodes. Numbering of nodes are very important. The practice generally we follow is, first we number the corner node. This is node number 1, this is node number 2, this is node number 3, and this is node number 4. First the corner node in a counter anti-clockwise direction. Then this side node, node number 5, then node number 6, node number 7, and node number 8. Okay, and this is again minus 1 minus 1, this is again 1 and minus 1, this is 1 1, and this is minus 1 and 1. Okay, and if you see the coordinates of other nodes, say node number 5, the coordinate will be, this will be 0 and minus 1, coordinate of node number 6 will be 1 and 0, coordinate of node number 7 will be 0 and 1, 0 and 1, and finally coordinate of node number 8 will be minus 1 and 0. Now I want to construct a function for n1, suppose n1. Okay, now so let's do it here so that we will have some space. So for n1, right, n1, what are the conditions n1 must have? First condition is n1 is equal to 0, n1 is equal to 0 at xi is equal to 1. Xi is equal to 1 means all this line, 3, 2, 2, 3, 6 line, means this line. This point, this point, this point, this point, n1 must be equal to 0. Then second condition is n1 is equal to 0 at eta is equal to 1, means at this point, and this point, right? So all these boundary nodes 2, 6, 3, 7, 4, these two condition ensures that the shape function, the n1 is 0. But n1 is also 0 at node number 5 and node number 8. Okay, so n1 is also 0 along this line. Okay. Now, what is the equation of this line? So n1 is, so third condition is n1 is also 0 along 5 and 8, node number 5 and 8, 5 and 8. And what is that equation? Equation of that line? Equation of that line is xi plus eta plus 1 is equal to 0. Okay, so n1 should be such that it satisfies this condition. Okay. Now the fourth condition is, so these three, these 1, 2 and 3, these will ensure that n1, all other nodes other than n1 shape function is 0. Now the last condition to be invoked is, at node number 1, n1 should be 1. So n1 should be equal to 1 at xi is equal to minus 1 and eta is equal to minus 1. So now from condition number 1 we can say, so let us assume some expression for n1. n1 is equal to some constant c, and then first condition tells me that the expression of n1 must have 1 minus xi term. Second condition tells me it must have 1 minus eta term, and third condition tells me it must have 1 plus xi plus eta term. Okay, so this is the expression of n1. Now, so this from first three conditions. Now the third condition tells me n1 at xi is equal to minus 1 and eta is equal to minus 1, that should be equal to 1. So this, if you substitute, then it will be c into 1 minus 1, 2, then 1 minus 1, again 2, and then 1 plus xi, 1 minus xi, means this is minus 1. This is minus 1, right? This is 1. This is 1. that is equal to 1. No, this is plus, so this should be equal to minus 1. Okay, so this gives us C is equal to minus 1 by 4, and with that we can obtain N1 is equal to minus 1 by 4 into 1 minus xi, then 1 minus eta, and 1 plus xi plus eta. This is the expression for N1. Okay. Now same thing we can do it for other node. Let's do that exercise for node number 5 once again. So let us write the conditions here. This is for node number 1. Let us write for node number 5 now. Node number 5. Let us write the condition. Condition is what? N5 should be 0. N5 should be 0 at xi is equal to 1, means on this line 2, 6, 3 line. Then second condition is N5 should be 0 at eta is equal to 1. Eta is equal to 1, which is 3, 7, 4 line. Then third condition is N5 should be equal. So this condition tells you that node number 2, node number 6, node number 3, 7, 4. These node n is N5 is equal to 0, and N5 is also 0 at node number 1 and 8. So N5 is equal to also 0 at xi is equal to minus 1. Xi is equal to minus 1. So this gives you this line 1, 8, 4. And then fourth condition is N5 is equal to 1 at xi is equal to 0 and xi is equal to 0 and eta is equal to minus 1. Eta is equal to minus 1. Now then expression of N5, let's take expression of N5 is equal to C into, it must contain expression 1 minus xi, that is from this equation. It must contains 1 minus eta, that is from this expression. It must contain 1 plus xi, this is from this expression. Then if we substitute N5 is equal to this from the fourth condition, we will get that C is equal to, this condition gives me C is equal to half. So expression of C will be half. This will be the expression for N5. So this is how the shape function can be obtained for serendipity elements. So same exercise we can do for other nodes, and similar exercise we can do for other serendipity elements as well. Okay, these other elements as well. Okay, so this is why this element was coined as serendipity element. It was, the shape functions are obtained just by looking at it. Okay, now so before we close, conforming is one. It is not very different than the continuity we had already discussed, but just for the completeness, because this is the term that you will see in any finite element book. The conforming element means, we had already discussed this. Conforming element means when the choice of nodal points, element geometry and local interpolation function, okay, leads to a global interpolant that is continuous across the inter-element boundaries. We had already discussed what is global interpolation, global approximation, and what is the minimum continuity requirement in finite element formulation if you see the global approximation. So the conforming element means if the points, the nodal points we have taken, the element geometry we have taken, and on that element geometry how the shape function, the interpolation functions are constructed, if all together give us an interpolation, global interpolation, which is continuous across the inter-element boundaries, then the individual finite elements are said to be conforming. Okay. Now, all these discussion we have so far, this we have derived the shape functions for shape functions of elements in Lagrange family, where only the interpolation of primary variable is the constraint, right? And we had seen if we have the interpolation only of the primary variable, then the global continuity is seen not. So Lagrange families of finite elements we have discussed so far contain C0 conforming elements. All the elements we have in this family are C0 conforming. What is C0 conforming, C0 continuity, we had already discussed. Now, the reason why I mention this may not be sufficient in many problems. Some of the problems will be doing, such as plane strain problem, plane stress idealization problem. We'll see in the next week. It may work for some of the problem, but for some problem we require higher order continuity. For instance, when you construct a shape function for bar element, we use Lagrange approach. That is the member of Lagrange families. But for the beam, we needed higher order continuity. There the slopes are also interpolated, the derivatives are also interpolated, and we also need, suppose if we want to analyze plates and shells problem, we will see that interelement boundary, it is not just the primary variable, their derivatives are also to be, or we have to make the derivatives also continuous. And that kind of element, which has the degree of which the order of continuity is more, is necessary for some problems, and there the derivatives are also to be interpolated. And that class of finite elements called Hermite families we have not discussed in the context of two-dimensional problem. In one-dimensional problem, it was extensively discussed how to construct a shape function for a beam problem, which is a member of this family. But for two-dimensional problem as well, we may need the interpolation of derivatives. Okay, that all depends on the problem that we are solving, the order of differential equation, and the weak form. Now, with this, let us stop here today. We have not discussed the shape functions for triangular element. We have already discussed for shape function for constant strain triangle, but other triangle, for instance, linear strain triangle, and then the natural coordinate in triangular for triangular elements, we have not discussed that. We will revisit the discussion on shape function probably in the 10th week, when we talk about implementation of two-dimensional problem with emphasis on computer implementation. There we will discuss the shape functions for triangular elements. Now, next class, what we will do is, next two lectures we will focus on integration. Integration is one of the important aspect. Once we have the shape functions defined over the parametric element, we will see in the next week how this shape function, how to construct this map from the parametric element to the physical element. We will do that. But then another important aspect is the integration, because integration we have eventually in the weak form that needs to be integrated, and most of the time because of this mapping we will see that integration may not be it may not be possible to have integration in closed form, and there we need integration, there we need to do integration numerically. So next two lecture we will discuss on numerical integration. Another interesting thing is, there also we will see that integration weights and the integration points that we use, they are defined in parametric domain. Okay. With this, let us stop here today. See you in the next class. Thank you.